Hi, everyone. Welcome to session 2 of the Great Lakes Coastal Wetlands webinar series hosted by Environment and Climate Change Canada and Toronto and Region Conservation Authority. My name is Sharon Lamb, and it is my pleasure to moderate today's webinar. I'm a project manager with the Ecosystem and Climate Science team at Toronto and Region Conservation Authority, and I'm joined by an amazing group of colleagues in both ECCC and TRCA, some of whom you'll meet over the course of this afternoon. Let me begin by taking a moment to respectfully acknowledge that all of us at this virtual meeting, no matter where we are located on land that has been home to Indigenous nations since time immemorial. We respectfully acknowledge that the lands we are situated on are traditional territories and treaty lands, in particular those of the Mississaugas of the Credit, the Anishinaabe of the Williams Treaty First Nations, the Huron-Wendat, the Haudenosaunee, and are now home to many diverse First Nations, Inuit, and Métis peoples. We appreciate and respect the history and diversity of the land and are grateful to have the opportunity to work and meet in this territory. And we are honored to be joined by representatives of Indigenous organizations at today's webinar. Let's now go over some quick housekeeping notes. Today's session is being recorded, and a copy of the recording and slides will be shared with all of you in a couple of weeks following the completion of the webinar series. All participants are muted and video disabled to minimize disruption and save bandwidth and emissions. Please use the Q&A box at the bottom of your Zoom control panel to post questions throughout today's session. You can also upvote others' questions in the Q&A. To share comments, please use the chat, and thank you to all of you for sharing with us in the chat your name and where you're calling from today. Closed captioning is available in English, and you can enable or disable this by clicking the CC icon at the bottom of your Zoom control panel. If you encounter any technical issues with Zoom, please send an email to Jessica for support. And with that, let's now take a look at what we have planned for you over this week-long 5-part webinar series. The first 2 webinars, yesterday and today, focus on sharing the results of Environment and Climate Change Canada's Great Lakes Coastal Wetlands Climate Change Vulnerability Assessment. Yesterday's session was focused on the results of the climate, lake level, and wetland response modeling developed by Environment and Climate Change Canada. If you missed yesterday's session, we do hope that you'll check out the recording once it is available in a couple of weeks. Today's session will focus on the remaining results from the vulnerability assessment, including wetland sensitivity, adaptive capacity, and overall vulnerability. Over the course of sessions 3 to 5 from tomorrow to Friday, we will explore different climate change adaptation strategies and options to enhance the resilience of Great Lakes coastal wetlands with guest speakers from across the Great Lakes Basin. And Jessica has shared a link to the detailed agenda in the chat, and hopefully you'll be able to join us for these upcoming sessions as well. Through these webinars, we hope to engage coastal wetland practitioners, describe Environment and Climate Change Canada's vulnerability assessment modeling and analysis, share the results of the climate and water level projections, wetland sensitivity, adaptive capacity, and vulnerability, and explore best adaptation strategies and options to enhance coastal wetland resilience. So with that, let's take a closer look at what we have in store for you today. We will begin with a presentation by Greg Main, who will provide an overview, or for some of you, a recap of Environment and Climate Change Canada's Assessing and Enhancing the Resilience of Great Lakes Coastal Wetlands project. We will then hear from Greg Grabus about the assessment of coastal wetland sensitivity to climate change for the 20 coastal wetland study sites. We will then take a quick 5-minute break for 2 more presentations. One is with Morgan Rennick on the assessment of coastal wetland adaptive capacity for the 20 coastal wetlands, and the other is with Patrick Rivers, who will help us bring the different components of the vulnerability assessment from yesterday and today together by presenting a summary of overall vulnerability of the 20 wetland sites. We'll be taking a few questions after each of the presentations as time allows, and we'll also have a collective panel discussion at the end. So please input your questions in the Q&A throughout the presentations, and where possible, please direct your questions to specific speakers. I will now invite Greg to share his screen while I provide a brief introduction to Greg Main. Greg Main is the Habitat and Species Unit Head with Environment and Climate Change Canada's Great Lakes Ecosystem Management Section. Greg began his career as a biologist with the province and later as wildlife toxicologist with the Canadian Wildlife Service. Since 2004, Greg has co-developed various Great Lakes plans, including lake-wide action and management plans, biodiversity conservation strategies, baseline coastal habitats, initiatives for community-based action, and most recently on coastal wetland vulnerability, resilience, and adaptation. And Greg, I see that your presentation is now up and in presentation mode, so I'll pass the floor over now to you.
Thanks, Sharon, and good afternoon, everyone, and welcome to day 2 of our 5-day webinar series. Once again, I'm happy to kick off the day with just a few slides to recap what we heard about yesterday, and also to preface today's presentations on wetland sensitivity, adaptive capacity, and vulnerability. Our study, assessing and enhancing the resilience of Great Lakes coastal wetlands, was supported by the Great Lakes Protection Initiative. And this helps us to address our joint domestic and binational priorities for the Great Lakes. So on behalf of our wetland working group, we hope that you enjoyed today's presentation and appreciate our synthesis of methods and results. So I'll begin by saying it's safe to say that our experience is changing Great Lakes climate. The impacts to coastal wetlands and coastal habitats are certainly evident when considering the frequent and intense storm events, pollutant runoff, extremes in lake levels, erosion of shorelines and wetlands and other coastal habitats, and temperature extremes. To confront the unknowns of future possible risks and impacts to coastal wetland resources, our team worked to achieve a number of goals and outcomes. Yesterday, we shared plausible climate and lake level trends and the methods and results for a coastal wetland response model. Today, we will share other results from our wetland vulnerability assessment, and in its entirety, our project in this webinar series adds to our engagement efforts over the years to improve the awareness of climate change and our study approach of what's at risk to Great Lakes freshwater ecosystem and best approaches for adaptation to climate change. I'll reiterate that this study would not have been possible without the hard work and commitment of scientists, modelers, biologists, and coordinators from 4 different branches within Environment and Climate Change Canada. Yesterday, we heard from staff from the Meteorological Service of Canada. Today, you'll hear from the Canadian Wildlife Service and the Wildlife Landscape Science Directorate, as well as the Strategic Policy Branch. You've seen this yesterday, but once again, this is by no means a complete list, but the purpose of this slide is to thank many of you for your support and participation in this project. We had the help from property owners, First Nation communities, and staff from provincial and national parks during field surveys. The province, university scientists, and consultants helped with spatial data analysis and provided insight on our study approach. And many of you provided input through our workshops, questionnaires, interviews, focus group discussions, and expert reviews. So we appreciate your involvement. So as promised, all I'm really intending to do right now is to give you a brief recap. Much of the content that I had shown you yesterday will be covered by Patrick and Greg. So I'm in an effort to reduce redundancy, I'll just refresh your memories. So the take-home message from Frank Sagliniak's talk yesterday on downscaled climate modeling and lake level modeling is that the trends in temperature, precipitation, and evaporation previously observed across the Great Lakes Basin will likely continue based on modeled results under the high and intermediate greenhouse gas emission scenario. Lake levels are projected to increase in variability, resulting in both more extreme highs and low lake levels. This is most pronounced under the higher greenhouse gas emission scenario, representative conservation pathway 8.5 shown in this graph and in the red line. Recall that projections are just that. The actual changes will depend on how society reacts or chooses to react through climate mitigation and adaptation. We also learned how our modelers developed an integrative coastal wetland response model that links the many physical components of the Great Lakes with wetland vegetation class distribution. An evaluation of possible climate change impacts were completed for 20 coastal wetlands across the Canadian Great Lakes Basin. And you'll see this in maps from in our subsequent presentations. This schematic here shows that several models were used in the coastal wetland response modeling exercise. Lake level models, hydrodynamic models, wave models, digital elevation models, wetland succession models, plus invasive species models that will be presented on Thursday. You also learned that the modelers used the representative concentration pathway 4.5. That's the intermediate emission scenario wherein the greenhouse gas emissions peak around 2040 and then start to decline around 2045. The modeling results were expressed using lower bounds and upper bounds of projected lake levels. Using the upper and lower bounds captures a broader range of possible changes expected by up until the end of the century. Model outputs include visualizations of coastal wetland class transition through time, showing possible gains, and in this example, in the green, as well as possible losses in red. The example shown here is for Long Point on Lake Erie, and the loss of emergent marsh and wet meadow, especially under the upper bound scenario of higher lake levels. In general, total wetland areas is projected to decrease to a greater extent under the upper bound climate scenario, that is higher lake levels, shown by the tan colored data points on the lower part of this figure. Note also that there are some projected increases under the lower bound lake level scenario in blue colored data points, but not to the same degree. I don't want to share too many details because I don't want to scoop my colleagues who are about to present. Before I turn it over to our next speaker, I just want to remind the audience that we set out to examine wetland resilience. We did so by first understanding wetland vulnerability to projected climate change. Again, yesterday you learned about how we deconstructed the complexity of vulnerability into its key components. Our speakers today will provide excellent information on climate, or I'm sorry, the speakers yesterday provided excellent information on climate exposure and wetland response modeling. And today we move ahead and our presenters will share information on how wetland sensitivity and wetland adaptive capacity were assessed, and finally, how overall wetland vulnerability was determined. So with that introduction, albeit very brief, I'd like to pass it over to my team members, or to Sharon first. And thank you once again for joining this webinar session. We hope that you learn a lot and appreciate the work that went into this study. So back to you, Sharon.
Thank you so much for the great overview, Greg. And next, we'll hear from another Greg, Greg Grabus. Greg, please go ahead and share your screen while I provide a brief introduction. Greg Grabus is the head of the Habitat Assessment and Data Management Unit at the Canadian Wildlife Service in Ontario region. He has been a wetland ecologist for over 25 years and has been involved in Great Lakes coastal wetland science throughout his career. Greg has focused on developing and implementing methods to monitor and report on coastal wetland habitat condition in relation to human-related disturbance and water level regulation. And Greg, I see that you're all good to go. The presentation looks great in presentation mode, so the floor is yours.
Okay, thanks, Sharon. So I would like to start off by drawing your attention to the contributors line on this presentation. My name is Last, and because of that, I would like to acknowledge basically the intellectual horsepower that was invested by the rest of the folks that contributed to assessing the sensitivity of Great Lakes coastal wetlands to climate change and their contributions. So assessing the sensitivity, so why do we want to do that? Well, it's because number one, coastal wetlands, they're great pockets of biodiversity around the Great Lakes ecosystem. Support all kinds of wildlife habitat, as we can see here. And there's a lot of concern about number one, coastal wetlands. Number two, the effects of climate change on coastal wetlands. So there's a lot of concern about the biodiversity, but we don't really, up until now, have a good idea, at least on the Canadian side, what we might expect through climate change. So that's why we took on this study to assess climate change. Now, here's another image of the framework we used that was modified from Glick and others. Today, I'll be talking about the sensitivity aspect, and Morgan will talk about the adaptive capacity. Pat will be talking about vulnerability. And we already saw about exposure yesterday. So of course, that exposure and that sensitivity together, that's the impact. And I'll be talking about that, but quickly we'll go back to the exposure part. And I know Greg reiterated this a little bit, but it's in my presentation, so I'm going to go through with it. Saw yesterday the cutting edge science that was presented by my colleagues at the Meteorological Service in the hydrodynamics and ecohydraulics section. Basically, they forecasted the response of Great Lakes coastal wetlands to climate change. So they developed this hindcast, and we can see here it was from the 1980s to late 2000 or 2008 or so. And they developed this model. They used climate, hydrodynamics, including water levels, waves, vegetation, land use, and elevation, and all, as well as air photos, classified other imagery that's classified and fed into this model. And they created a forecast to the end of the century. And for this sensitivity assessment, we were able to use the dates we see here, which is 2071 to 2098. So that's 28 years inclusive that we used for the sensitivity assessment. The reason I draw your attention to that is because those 28 years are going to come up later on in the presentation. So they gave us these forecasts, but they gave it to us for two different scenarios under representative pathway 4.5. And the way I think about it is, if you're planning your weekend, you're going to go to the park, have a picnic, you look at the weather forecast and it says 80% chance of rain. You look at another app that says 40%. Well, they're both based on base data. It's just that the different weather forecasters use different models. And that's kind of what we saw here, right? So I was presented with data from an upper bound. And just to reiterate, those water levels, they were similar to long-term average water levels. And we also had an upper bound where the average water levels were higher than the long-term average we've seen. Now, I've just generalized across three Great Lakes, Lake St. Clair and the connecting channels, but that's basically what we're seeing. And the other thing to point out is that both these scenarios showed increased variability in general over those timelines. So that was an increased incidence of extreme highs and extreme lows. So why are extreme highs and extreme lows important in this case? Well, it's because wetland vegetation grows according to its hydrologic tolerance. And just to familiarize you with this, the way I start the conversation usually is those water lilies over here on the bottom, on the right-hand side, they don't grow up on the hill because they'll dry out and die. And these trees up here on the left-hand side, they don't grow fully submerged in the water because they'll die. And that's because the vegetation grows according to its water tolerance. And that goes for the trees and the water lilies, as well as all the other vegetation species along this hydrologic gradient or along this elevation gradient of a wetland. So different species will grow according to different water level tolerance, and being scientists, we like to group them, and we've done that. And you can see in the slide here, and this is the information that I received from the Coastal Wetland Response Model, was information on the submerged aquatic vegetation community, the emergent marsh, the wet meadow, which we also call meadow marsh, and then the different types of swamp, treat swamp, shrub swamp, or swamp overall. And the information that was given to us for these communities, it was all digital, but this is the visual representation of it. And this is the visual representation of, you can see this kind of picture matrix here with the lower bound, the upper bound for Airport Creek, which is in Tyendinaga-Mohawk territory on the Bay of Quinte and Lake Ontario. And we see for the vegetation communities, the submerged aquatic vegetation communities, sometimes we just call it SAV, and for the emergent marsh. And the colors here represent I think these are actually changes in the communities, but this is the kind of information we got, not just for Airport Creek, we got it for 20 coastal wetlands around the lower Great Lakes, so Huron, Erie, and Ontario. And regrettably, as explained yesterday, not Lake Superior. We just ran into complications in terms of resources. But we did get information for these 20 coastal wetlands. So within these wetlands, so of course, we're talking about sensitivity, what aspects or what were we really concerned about when it came to sensitivity? If you saw some of the other slides, we basically chose wetland or habitat attributes, because all we got, as you saw, was the vegetation data. We didn't get anything on wildlife or the affinity to wildlife to these different wetlands under climate change, only habitat as it pertains to vegetation species. So we identified these elements of biodiversity that we wanted to report on and actually look at the sensitivity of them. The area of the wetland, the area of the meadow marsh or wet meadow, wetland interspersion, the volume of the submerged aquatic vegetation community, and the diversity of different wetland communities within the wetlands. So those different submerged aquatic vegetation, meadow marsh, emergent, all those. So let's start with wetland area. So the reason wetland area is important, as you can see on the two graphs here, the one on the left, this study demonstrates that the total species richest, so the total number of plant species at wetlands is generally higher at larger wetlands. And on the right, we can see this study here that there tends to be a larger abundance of marsh bird species at larger wetlands. So the size of wetlands is really important in terms of their capacity to support both vegetation species and not just bird species, but other wetland taxa. This relationship has been demonstrated there. I just chose to show these two graphs. The second thing is the meadow marsh that we looked at. Now that's that community or the wet meadow that's sandwiched here in between the other vegetation types at the within coastal wetlands in general. And there's a picture of Michael in a meadow marsh, a particularly ferny meadow marsh. But we looked at meadow marsh because, as I mentioned, it's sandwiched in between these other vegetation types, and anything that's going on with those vegetation types in terms of their advancement upslope or downslope is generally affects the meadow marsh. So you can get advancement or whatever establishment of woody or shrub vegetation downslope into that meadow marsh during drier years, and during wetter years, you can get establishment of emergent vegetation into that meadow marsh. And it really is the way I see it anyway, in my experience, is kind of like a canary in the coal mine. If something's happening with your meadow marsh, there's generally things happening with the habitat throughout the whole marsh. And not only that, but it's a key performance indicator for Lake Ontario, which is regulated. So there's a Lake Ontario Adaptive Management Monitoring Plan, and meadow marsh is a key performance indicator. Not only that, but certain bird species like American bitter and even mallards, swamp sparrows, have been shown to have a particular affinity to meadow marsh. The next element we looked at was wetland interspersion, and in the background you see a good depiction of it. So basically it's the mixture, or I guess it's the balance of between open water and vegetation within a wetland. And in the schematic that popped up in front of that photo, you can see on the left-hand side just a small water pocket on that one wetland that's low interspersion, whereas the picture on the right that has a lot of water intermixed with the vegetation, that's high interspersion. And studies have shown that wetlands with higher interspersion tend to support, or at least, they tend to support or attract marsh bird species, an increased number of marsh bird species, and things like American bitter and Sora rails, Virginia rails, as well as species at risk like least bitterns. The submerged aquatic vegetation zone is also important because, well, it's great habitat for things like fish you can see in this picture, reptiles like turtles, amphibians, particularly in their larval stage, the tadpoles, as well as other species like aquatic macroinvertebrates. And there's a lot of evidence, or at least there's emerging evidence to show this, not just the aerial extent of the submerged aquatic vegetation zone within a coastal wetland that's important, but more so the actual volume, which makes sense, that submerged aquatic vegetation can occupy. So that's why we didn't look at just the area of the submerged aquatic vegetation zone, but the actual the volume of it. And there's another study that shows that Great Lakes coastal wetlands, at least lower Great Lakes ones with submerged aquatic vegetation communities in good condition, tend to support bird communities that are also in good condition. The last element that we looked at was the diversity of vegetation communities. So in this picture of Cranberry Marsh on Lake Ontario and Whitby, you can see the different vegetation types. So we see some meadow around the top edge here, this light greenish yellow. There's a pocket of submerged vegetation in here. There's emergent vegetation throughout this marsh, and then a pocket of shrubs on the south end of the wetland and also along the barrier beach. And the reason we looked at the diversity of vegetation communities is, well, different vegetation communities support different types of wildlife taxa or different species of wildlife. Here's a study that shows the differences in habitat preferred by sedge wren and marsh wren. I think it's in the upper Great Lakes. And then here's another one that shows the affinity of 7 turtle species to vegetation types across the Great Lakes. So those are the elements we looked at when considering the sensitivity. So we had to take these and basically operationalize what does sensitivity mean in the context of these habitat attributes of wetlands. So the first thing we had to do is define sensitivity, to say actually what it was. The second part was you had to take that definition and really operationalize it in terms of the data and determine what the sensitivity of each of those wetland attributes was at each of the study wetlands. And then we thought it would be a good idea to combine the sensitivity attributes at each wetland to derive an overall sensitivity score, right? So it'd just be one score of sensitivity for the wetland and with a color map, easily understood, but still with a strong ecological and analytical underpinning. So the definition of sensitivity, well, we're better to go than the Intergovernmental Panel on Climate Change, right? And their definition of vulnerability says it's the propensity of a system or a species to be adversely affected, and that vulnerability encompasses elements including sensitivity. Thank goodness, because I'm 14 minutes into the presentation. If sensitivity isn't here, I don't know why I would be. And it says, or susceptibility to harm, right? So it's a negative thing, or the lack of capacity to cope and adapt. So we took that definition in terms of sensitivity and operationalizing it. We said sensitivity for us in this study is going to be the degree to which a wetland adversely responds to climate change, right? It has to be adversely. And thinking back to those elements of coastal wetland habitat, the 5 that I talked about before, each of them, if there's more of it out of wetland, that's good. And if it decreases, that means that the wetland in general has a lower capacity to support wildlife and affords less habitat to any kind of wildlife. So if it's higher, it's good, we're seeing quotes, and if it's lower, that's worse. So how did we actually do this? Well, here's an example of, this is just fake data, but this is how we did it. Just to orient you to look on the left side in terms of determining this sensitivity, there's the wetland attribute. It could have been any of the wetland attributes that we looked at. Wetland area, volume of submerged aquatic vegetation. And of course, as I mentioned before, as water levels go up and down in the Great Lakes, which is natural, these different elements of coastal wetland habitat are going to respond. So they're variable. And this is what we see in this picture here, the imaginary hindcast that we got. It's variable. So what we did is we identified the 10th percentile in this data set, and that's represented by the dashed blue line. And anything under that 10th percentile was considered to be an extreme low. And we said anything in the future beyond or below, that extreme low is going to be due to climate change, because the only difference between these two data sets really is that our modelers had put in the influence of climate change. So all the red spots on the right here in our forecast are due to climate change. So basically, we just add those up and we compare them to the past and see how sensitive the wetland is. Of course, I'm going to elaborate on that, but I also like to point out that again, this we took our cues on this from what other folks had done and published in the literature in terms of determining sensitivity of natural systems. Now, as one of the fun parts, we actually get to see data that was derived. So these are real data at this point, and each of these graphs that I'm going to show you over the next 3 slides are for wetlands under the upper bound scenario. So that scenario that is wetter and and also more variable. So here we see Lind Creek Marsh, which is in Whitby on Lake Ontario, and we see in the hindcast on the left side that it's variable as expected. There are some extreme or some lows, but then we see, and your eyes have probably wandered already over to the forecast. It does look kind of like our sample data set, but about half of those points are below that 10th percentile. So we see some extreme lows in that, or we could see some extreme lows in the future if we realize that upper bound scenario. Here's another example of Anderson Creek. It's up on the north channel of Lake Huron. And we see there's not as much variability in the high cast, but that forecast, we actually see during the upper bound that there's not many times, if at all, that wetland area dips below that 10th percentile. So overall, we'd expect to see an increase under this scenario in wetland size for Anderson Creek. And the third one I'm going to show, lamentably, is Long Point National Wildlife Area, where we see, again, a lot of variability in the hindcast, but then the projection into the future under the upper bound scenario, we see all points are actually lower than our extreme low threshold. And this carries through this carries through to other things. So this is the kind of thing we didn't actually visually do, that we did it using script. This is how we examined the data sets. And we chose, so we added up. This is how we actually developed the sensitivity score. So if you look over to the right here, it shows the ecosystem attribute and the number of extreme years that we saw. So this is example data again. So we saw 22 years of extreme decrease in wetland area. So we put the 22 over here. I hope you can see the arrow. 12 years of extremely low meadow marsh area, 18 for interspersion, 7 submerged aquatic vegetation, and 14 for the diversity. So those are all added up, the numerator here, and we divide by 140. That's the 28 years for each of these that we modeled, each of these times 5. So 28 times 5 is 140. So basically you divide it, and it says example because it's example data. It's 0.52. And that's the proportion over all the modeled years for each ecosystem attribute, the proportion of the projected extreme years. So as you can see here, that'll range from 0 if you had no extreme years for all the wetland attributes to 1. And that's if all wetland attributes were extreme in all years. Of course, all the data falls between 0 and 1. So we went a step farther in terms of developing the sensitivity score, and we wanted to associate a bit of a heat map or some categories with the sensitivity measures. So if you see over on the left side here, the less than 10%, right? So anything, if we had a combined number of extreme hindcast years that was below 10%, remember we used the 10th percentile? Well, if it was below that, then it was actually no different than our hindcast. So we said that on the right was low. That was a low risk. It was between 0.1 and 0.55 or 55% extreme years across all the modeled years for all the attributes. We said that's medium or at risk, and that's yellow. And then if it was above 55, it was critically at risk, and we designated that as red or high. Now, again, with these numbers, could we have chosen different numbers or changed them? Yes, we could, except for the 10%, we could have used different ones. But again, we took our cues from what had been done for past studies in terms of scoring sensitivity in natural systems. So now that now that I've showed you how we actually combined all the data, the next slide I'm going to show you is real data, but it's actually separated out. So I'll orient you to the figure here. On the left, we have, so this is the combined attribute sensitivity across all 20 wetland sites. And I put on the 10th percentile here, so just as a benchmark for us. And then on the x-axis, we can see those all the different habitat attributes, and this is for the lower bound. So this is what we found. So my interpretation, well, so hold on, let me just wait for a sec before my interpretation. I'll go through these boxes, right? These dashes in the middle of the box, that's the median of the data set, which is the central tendency of the data, not unlike an average. And then the boxes, basically the boxes and the whiskers and the dots represent the range of the data. So again, back, my interpretation of this lower bound is that we are expecting to see instances where we get extreme lows across these wetland sites and interspersion, meadow marsh, submerged aquatic vegetation, and maybe diversity, but not in total wetland area. So we do have some extremes, particularly in meadow marsh area. It looks like there's some sites that are expected to lose under their lower bound, the meadow marsh area. But if you attended yesterday's talks and the talk about the upper bound, as you might imagine, is a bit more extreme in terms of what we're seeing. So again, it is a bit different in terms of interspersion, the volume of submerged aquatic vegetation, and wetland diversity. We are expected to have increased times when they are more frequent times when they're lower than in the past and then the hindcast. But you probably can already see from the graph, we expect to see, we realize that upper bound scenario, there's going to be quite a frequency of times where there is an extreme loss of total wetland area and wetland meadow marsh or wet meadow in those wetlands. And you can see that the range actually goes up to the 1 in some of these. So in some cases, we'd expect to see, decrease below the 10th percentile for the whole slice of time that we looked at. It doesn't mean the wetland totally disappears. It just means it's below that 10th percentile. So now I'm going to group the data again. So taking these data and actually showing you combining the risk, and we have again, so these are those risk categories that I showed you in terms of and how we develop them. So we have the number of wetland sites here on the left, and then the total sensitivity are the bars here, low risk, at risk, and critically at risk for each one. So we see under the lower bound, 4 sites are expected to be at low risk, whereas the other 16 are going to be at medium risk. And when we move to the upper bound, we see just 1 site that's expected to be at low risk. And incidentally, that one that's low risk is not the same as the one over here. It's a completely different site. And then we have, I think, 14 in medium risk, and then another 4 or 5, sorry, that are expected to be critically at risk under that upper bound scenario. Same data, except now we get to see it by site. So there's maybe 3 things I wanted to draw your attention to here. One is on the right side of the graph. We have again, it's arranged by site and the sensitivity range. So on the right side of the graph, we see a large variation or difference between the amount of risk we might see in sensitivity between the upper and lower bound, which is just say those bars on the right hand side are pretty long. The second thing I'd like to point out is that in some cases it's not. For example, for Jordan Station, which is here, which is on the Niagara Peninsula in Lake Ontario, and maybe Francis Point, which is Eastern Georgian Bay, there's actually not too much of a difference between that upper and lower bound. And then the third thing I'd like to point out is, of course, there's always got to be some sites that are different than everybody else. And these ones are upside down, where we actually see where we'd expect to see lower risk during the upper bound scenario than we would during the lower bound. And that's for Airport Creek and for Anderson Creek. And the reason I think we're seeing this is because both those sites basically have the ability to migrate upland during higher water levels. And of course, we can sit and look at this graph all day and pick out different things, but those are the main things I wanted to demonstrate here. So now we take all these data and map them this time. This is what we see across the Great Lakes. And sorry, I apologize if you can't discern the colors. They're all yellow except for this site here, South Bay in Lake Ontario, Lind Creek, Selkirk Provincial Park, and I think this is Treasure Bay up in Lake Huron. The rest are yellow. That's for the lower bound scenario. And when we graph these by the heat map in the upper bound scenario, we only get one site, which is Airport Creek, that's low risk. The rest are going to be yellow, except for the red ones, obviously, which is Long Point Provincial or Long Point National Wildlife Area. And then a lot of the sites down on the Huron-Erie corridor. So in the Detroit River, and Lake St. Clair and Johnson's Bay, which is on Whipple Island First Nation, and also Whiskey Harbor, which is in Wikwemicong and Ceded First Nation up on Manitoulin Island. But there's a bit of still some questions over that Wikwemicong analysis, and that we weren't able to really see how far the wetland could migrate uphill. So it was a bit constrained. It may have influenced those results. So I think we talked a little bit about this yesterday, and it was, why are we seeing so many differences across these different wetlands? And I think it was explained a bit throughout the presentations as well as the questions yesterday. And if you think back to some of the photos of coastal wetlands, the study wetlands I've showed you, they're all kind of different shapes. They all look different. They have different topography and bathymetry. So their contours, they have different exposure to wind and waves. They're surrounded by different land use and geomorphology. So, which is to say that in the analysis that was done during periods of high water levels, it may have precluded the wetlands from migrating upslope. Number one, because there's some kind of development, transportation, infrastructure, residential, industrial, urban development, or it could be a natural kind of block. And I think Morgan might get more into this in terms of, in this case, that you see the picture here on on Long Point and Lake Erie. There's a lot of sand dunes on these different fingers you see in the wetland, and it may preclude the migration of that wetland upslope. So maybe just to draw your attention to the figure a little more closely, this is the hindcast for part of Long Point, and on the top we see it's basically just divided into wetland, upland, and open water. But then we look at the lower during a high water level scenario, basically that wetland is getting flooded out. The water is just rising too fast and too high to support wetland habitat. So I would like to end off with just the take-home points, right? We saw under both scenarios that all our study sites are projected to be at least at risk under RCP 4.5. And we also saw that the sites that are projected to be more adversely affected during that upper bound, we're seeing an increase in water levels and lots of variability. From the box and whisker plot I showed you, it looks like the wetlands are mostly going to be at risk due to loss of area, and it could be area of that meadow marsh or overall area. Again, we're not expected to see them completely wiped out or completely lost. It's just going to be lower than we've seen in the past. And then if you're interested in the 80-page report, in contrast to the Coastal Wetland Response Model report, that was 500 pages and easier read, I think would be the 80-page report that we're expecting to have on our publication site later this spring. So I'd like to just thank everybody for attending and being here to listen to our approach on sensitivity.
Thank you for the excellent presentation, Greg. We do have a couple of minutes to take some questions before the break. So why don't we pose a few questions to you now before we end, and then re-invite you to join our panel discussion at the end. So I'm sure there is a lot of questions from the audience. Please keep typing your questions into the Q&A box, and if we can't address them now, we will save them for the panel discussion at the end. So Greg, our first question is, did any of the sensitivity results surprise you at all, or did they unfold just as expected?
So when we started this, project, and I even told people this, but I was wrong. I said, you know, if we have two sites that are on the same lake and they're next to each other or kind of close to each other, and they have similar sensitivity, then I'm sure the sites that are close to it would have pretty much the same amount of sensitivity. And as I showed here, that's wrong. It really, the sensitivity is really site specific. And it doesn't depend, it depends more on the actual nature of that site than it depends on who its neighbors are or what lake it's on, and those things. So yeah, that was one of the things that surprised me. Yeah, it's good to be wrong, right? I guess you can learn things.
That's great. Another question for you, Greg, is you've clearly highlighted that each of these sensitivity indicators included in this study are supported by literature current frameworks. Are there any additional indicators of coastal wetland sensitivity that you think are important but weren't able to include in this assessment?
Wow, so I can almost hear the rest of my author list trying to channel me the answer to that. They considered a number of different wetland attributes, and we couldn't report on everything, and it had to be narrowed down to a certain suite, and it was 5. I don't recall what the other ones are, but we did consider other elements of wetland habitat diversity or biodiversity. I just don't recall what they all were, so I apologize.
No worries, Greg, and perhaps we can follow up with you and your author team for a response following this webinar. So one I see here is from Ryan. How much do invasive species contribute to wetland sensitivity?
So, oh, you know what? You need to wait for the next presentation on that. Morgan's going to talk about the adaptive capacity part. So in terms of sensitivity, we didn't consider it because it's too hard. And my take on that was we're controlling invasive species right now on Long Point and not just Long Point, a number of places across the lower Great Lakes. So, and this will go into another presentation that our colleagues from Meteorological Services in Quebec are going to present. I think it's either tomorrow or the next day on invasive species. So you'd want to tune into that. But as far as sensitivity goes, we didn't consider it because we weren't really sure how to, in that maybe people or maybe there'll be biocontrol, maybe there'll be other elements that are really going to affect this. So as far as the sensitivity aspect goes, we didn't really consider that. But again, for the sensitivity, you wait for the adaptive capacity talk.
That's great, Greg. And yes, we will be hearing from Morgan right after the break. And as Greg May noted in the chat, the invasive species modeling talk will be happening this Thursday by Marianne and Dominic. So hopefully you will be able to join us for that talk on Thursday on the models for cattails and Phragmites. And before we let you go, Greg, one last question. Based on your research and monitoring work, we wonder if you have an estimate of the number of plant species currently found within coastal wetlands across the Great Lakes, whether it's in Canada or binationally. Any good estimates of current plant species diversity in the Great Lakes coastal wetlands?
Yeah, so as far as species richness goes, those data are available, and not through necessarily through this project. We did do field-based surveys to determine basically what elevation or what water depth different species occur at across all our sites. But there is another program ongoing. It's a binational program. It's mostly funded through the US EPA, but it also has a Canadian component to it. We both US and Canadian sites are surveyed across the entire Great Lakes, including Lake Superior and Michigan in this case. And we're able to develop a species list from that. And I don't know if any of my colleagues are on here and can tell you what the number is. We've actually calculated what that number is. I don't remember what it is. I could say I know it's more than 200 species. Now, let's keep in mind too, that there are certain species that are a lot more common. So it's the old 80-20 rule, right? Like I think, well, I shouldn't say that. There's a certain proportion of species that represent the bulk of the species in a wetland. And then there are hundreds of other species that are not as common in wetlands, but we still see them. Anyway, maybe I've been left out. I don't know the exact number. Sorry. It's definitely doable. Maybe I can post it in the Q&A or something during the break.
That would be great. Would be looking forward to learning about that, Greg, if you can post it in the chat after the break. And with that, let's take a 5-minute health break to refresh before our last two presentations before the panel discussion. And right after the break, we'll hear from Morgan. And we are back. Morgan Rinnick received a Bachelor of Science with honors from the University of Guelph in 2013, a Master of Science in Environmental and Life Sciences in 2017 from Trent University, and a postgraduate diploma in Geographic Information Systems from Algonquin College in 2013. She joined Environment and Climate Change Canada as a fiscal scientist in 2018. Her research interests include remote sensing using unoccupied aerial vehicles, or UAV, invasive species monitoring in North American wetlands, and landscape toxicology. Morgan, I see that your slides are up and in full presentation mode, so I'll pass the floor to you.
Awesome. Thank you so much for that introduction. So yes, today I will be presenting a little bit on assessing wetland adaptive capacity in the Laurentian Great Lakes. So there's a couple of names on here. There's myself, Pauline, and Patrick. This project was definitely not completed individually. It required quite a bit of different inputs and different collaborations. And lots and lots of help from Pauline and Patrick, as well as our managers, Greg Main, Greg Grappis, and Jason Duffy. So a quick thank you to everybody who's involved in that. All right, so let's start at the beginning. The 20 wetland sites. So watching Greg's presentation, as well as for those of you who were here yesterday, I'm sure these 20 wetland sites are becoming more and more familiar. But the locations is exactly where we started for assessing wetland adaptive capacity. The 20 wetland sites are located across Lake Ontario, Lake Erie, and Lake Huron. And these wetland sites were selected based on a couple of things. They were selected based on their data availability, their range in anthropogenic disturbance, their economic and cultural significance, and their variability in hydrogeomorphology. So the end goal really of this overarching project is to assess wetland vulnerability. And in order to do that, we need to look at two different things. The first was sensitivity, which Greg just gave us a wonderful presentation on. And the second is adaptive capacity, which I'll be spending the rest of this presentation on. So the idea is that these two metrics come together to help us be able to identify which wetlands are the most vulnerable and which wetlands are a little bit more resilient. So for example, if you have a highly sensitive wetland or a moderately sensitive wetland, and they both have a low adaptive capacity, chances are they're going to be much more vulnerable to climate change. Similarly, if it has a high sensitivity and a moderate adaptive capacity, again, you're going to be having a very sensitive wetland. In the event that you have a wetland with low sensitivity and high adaptive capacity, these are going to be our much less vulnerable wetlands. So before we get too deep into the weeds, I just want to go over a quick definition of adaptive capacity. So there's several different definitions of adaptive capacity that are used depending on the fields of study that you're in. For this project, we've defined it as the ability of a wetland in its current state to adjust and maintain its current ecological regime under changing climate conditions, including variability and extremes. There's two parts of this definition that I'd like to highlight that may give it a slightly different definition compared to what you may have seen before in regards to adaptive capacity. The first is the reference of current state. So current state implies a contemporary time frame. While we're well aware that climate change is an ongoing challenge for wetland ecosystems, it can be really tempting to want to look at how wetland ecosystems existed before any impact was observed on them. So looking at their original undisturbed state. However, the reality is that wetland ecosystems have already been impacted, and we need to look at how they exist currently to better understand how they're going to respond in the future. The second term in the definition that I'd like to highlight is ecological regime. So by saying maintain ecological regime, this definition implies that an adaptive wetland has a greater ability to maintain the same structure, function, physical properties, and ecological services that it currently provides. So we're looking at its current state. We're looking that it can continue to provide the same ecological services given disturbance events that may happen in the future. Actually, before I move on, I'd also like to just draw attention to the fact that adaptive capacity is very much a theoretical concept because we're trying to assess how well a wetland is going to adapt to future disturbance events. There's no way of actually really verifying exactly how they're going to adapt. So it is a fairly theoretical aspect to measure. And for that reason, we elected to use a composite indicator methodology. Composite indicators, or CIs, are a unitless mathematical aggregation of quantitative variables. They're a simplified representation of a phenomena that cannot be directly measured, which is why this method lends itself so well to the production of an adaptive capacity score for our wetlands of interest. In general, there's 4 general steps that can be looked at for assessing a composite indicator. The first is selecting the variables that you want to use and going out and actually measuring them. Next is normalization of the variables. So you can imagine each of our different variables may have a different unit of measurement or may have a different data distribution. So the normalization of the variables allows us to actually combine them and directly compare them together. Third, the normalized data values are grouped according to their effect on adaptive capacity. And then the results can be reviewed, modified as necessary, and applied. All right, so starting off with that first step, the selection of the variables. Wetlands are highly dynamic, and there's an absolute ton of different variables that can be assessed for looking at how they can improve or reduce wetland adaptive capacity. And in an ideal world, we would be able to include all of them and we'd have a perfect representation of exactly what's going to happen to our wetland. However, we had to work around several limitations, and I'm sure almost everyone who works deals with these exact same limitations, and that is budget and time. There's only so much time and only so much money that you have to spend in order to complete this type of assessment. Therefore, we selected 3 overarching variable criteria that each of the variables included in this analysis had to meet in order to be used. So first, the variable must represent the current state of the wetland. As we touched on in the definition, making sure that the data that we're using does reflect the current state. So for example, there might be a wonderful data set, but it's more than 30 years old. Does that really represent the current state of the wetland right now? Maybe not. So looking at more contemporary data was an important factor to consider. Second, variables had to be measured using the exact same method across all wetland sites. So for example, assessing something like species diversity, the same sampling effort and the same resources had to be applied at all 20 sites. With respect to geospatial data, of which we used quite a bit of in this analysis, making sure that we're using the exact same spatial resolution or temporal resolution of our data was an important thing to consider. And the idea behind this is that you really don't want the underlying sampling effort or resolution of your data to be a factor contributing to what the end scoring is of your composite indicator. So for example, if a huge amount of sampling effort was put in at one site, that might reflect in a higher biodiversity, which isn't necessarily true. It's just a reflection of the amount of effort applied. So making sure that there was a consistent method across all sites was an important thing to consider. Finally, variables included must have a scientifically supported influence on wetland stability or plasticity. So because adaptive capacity is theoretical in nature, and it can't really be verified until one or more disturbance events have occurred, and of course, we would like to delay those disturbance events, each variable included had to have an established scientifically supported influence on wetland stability or plasticity. And this follows the logic that a decrease in wetland stability or its plasticity is going to reduce its ability to adapt to a disturbance event. Yeah, so even though adaptive capacity is theoretical in nature, we do have some good understanding of how these wetlands can respond to disturbance. And the idea was that each of the variables included had to have that clear connection to something that's going to help a wetland respond. So ultimately, we ended up with 8 different variables that met all 3 of these criteria. The first is vegetation species richness. The second is landscape conditions, so the condition of the area surrounding the wetlands. We also looked at invasive Phragmites locally, so that's invasive Phragmites australis within the wetland, as well as surrounding the wetland. We also looked at wetland migration potential upslope, so that's towards the land, and wetland migration potential downslope, so this is towards the water. And then the last 2 are protection locally, so within the wetland itself, and protection surrounding the wetland. So each selected variable had an expected directional impact on the overall adaptive capacity of the wetland. For example, natural land cover surrounding the wetland will improve native species population stability, which in turn is going to improve the ability for wetlands to adapt. Similarly, high species richness and low coverage of invasive Phragmites would improve adaptive capacity by increasing ecosystem stability and function. Similarly, a high potential to migrate both upslope, so towards the land, and downslope towards the lake, is a measure of physical plasticity, which, if high, is going to improve adaptive capacity. And finally, should the area within or surrounding the wetland have federal protection status, there's a higher probability of management and human mitigation, which theoretically would also improve wetland adaptation. So each of these variables was either directly measured by on-site sampling. So a good example of that is species richness, where we actually went out to the site and measured these variables. However, most of these are actually taken from geospatial data. So natural land cover, upslope and downslope migration, protected area locally and in the landscape were all geospatial data sets. So in using this theoretical framework, variables could then be grouped into sub-indicators according to their impact on adaptive capacity. So you can see here natural land cover corresponds with landscape condition, Phragmites within and surrounding the wetland, as well as vegetation species richness corresponds to biological conditions sub-indicator. Migration upslope and downslope both contribute to migration capacity, and protection contributes to conservation capacity. So one of the biggest things I think that might pop out to you is how do you deal with potential correlation within these variables? So for example, looking at a site that has a Phragmites invasion, chances are if there's a lot of Phragmites that exist there, the native species richness has probably dropped. So you may end up with something, basically relationships between the variables that are being included within one sub-indicator. So in order to address this, we applied a principal component analysis to determine the appropriate variable weightings for combining these variables to produce the sub-indicator. Normalized variables for each sub-indicator were then multiplied by the weights and summed. The sub-indicator variables of landscape condition, biological condition, and migration capacity were then multiplied to account for interactive effects. So as you may imagine, none of these sub-indicators are an island in and of themselves. They're going to be interacting with each other. So a good example of this might be if you have a site with really great migration capacity, but it doesn't have enough native species richness to colonize new areas that become either exposed through a drop in water level or maybe get pushed upland, then you might not end up with a very healthy wetland system in general. So having the interactive effects between each of these sub-indicators was accounted for through multiplication. Finally, the sub-indicator of conservation capacity was added after the combination of the other 3 sub-indicators, under the assumption that conservation or protection is going to modify what is already existing there. So a really good example of this might be at Long Point Wetland, where we know that there's an invasion of Phragmites. That might be improved by the addition of conservation, so conservation measures such as removal or treatment of invasive species. The final result of this aggregation is the relative score for adaptive capacity. This means that each resulting score allows for comparison and ranking of the 20 sites that were assessed. In the following slides, we're going to cover what each of the results were for these sub-indicators, as well as the overall adaptive capacity score for each of the 20 wetland sites. All right, so starting off with the first sub-indicator, which was landscape condition, which was composed of natural land cover. All right, so it was found that in Lake Huron, specifically Georgian Bay, as well as the St. Lawrence, had the highest had sites with the highest landscape condition, while the more southern wetland sites along Lake Erie and Lake Ontario had a poor landscape condition. And I think this result is pretty in line with what most people would expect. Most of our human population is focused in southern Ontario, which is where we end up with a lot more industrialization, a lot more agricultural practices, a lot more cities, towns, roadways, all these kinds of things that are going to reduce the overall landscape conditions surrounding these wetlands. Whereas in Georgian Bay, maybe there's a little bit less of that focus of population density. Regarding migration potential, so again, this is lakeward and landward migration. It was observed that wetlands along Lake Erie and Lake St. Clair had the highest migration potential, and this is likely due to the fine to medium grain sediments and shallow bathymetry of these areas. Wetland sites in Lake Huron and the St. Lawrence Channel had the lowest wetland migration potential. Low-scoring sites were often protected embayments in bedrock or had till-derived sediments, which explains some of their low migration potential. So yeah, lower migration potential up here, higher migration potential down and along Lake Erie. High biological condition, biological condition in general, which again was made up of species richness, vegetation species richness, as well as invasive Phragmites australis within and surrounding the wetlands, resulted in a noticeable higher biological condition found along Lake Huron and the St. Lawrence River, while lower scores were focused along the Huron-Erie corridor, so Lake St. Clair here and Lake Erie. The concentration of sites scoring very low for biological condition along the Huron-Erie corridor is likely due to the high amount of invasive species that exist there, invasive Phragmites. All right, so the sub-indicator protection. So again, this is protection within and surrounding the wetland. Only 7 of the 20 sites that were considered in this analysis had protection status, either within or surrounding them, as measured through the Canadian Protection and Conserved Areas database. However, due to variation in percent area of protection, both again within and surrounding the wetland, the 4 sites on Lake Erie, as well as the St. Lawrence, received a greater protection score compared to the 2 sites on Lake Huron. So we can see most of the protected areas are down here. Even though we had 2 that were in Georgian Bay area that were protected, because they had a lower amount of protection area, they didn't score quite as high. All right, so once we had all of the sub-indicators calculated and aggregated together, we end up with our final adaptive capacity score for each of the 20 wetland sites. So that's what we can see here. And it looks like we've got quite a good variety of high, low, and moderate scores all across most of the lakes. But you might notice that they're mostly concentrated, again, within that Huron-Erie corridor area, as well as the western portion of Lake Ontario. So those were the sites that had the lowest ability to adapt to climate change. We can actually take a look at Johnston Wetland, which is located on Lake St. Clair, as an example of a wetland site that is getting a low adaptive capacity score. So most of the sites that received lower scores scored poorly for generally 3 to 4 categories. So you can see here at Johnston Wetland, there's a low biological condition, again, likely due to the invasion of Phragmites. there's a low landscape condition, likely due to agricultural practices, and there's a low conservation capacity. However, this was one of our sites that had the highest migration potential. And I think this is a really good example of how scoring poorly in several categories can't really be compensated for just by one really highly adaptive category. So maybe this is their site with the best migration potential, but unfortunately it's still receiving a very low score because it scored poorly for the other categories. For low and moderate adaptive capacity, they're sort of scattered across all three of the lakes that we looked at. And this is a good indication that we are capturing quite a bit of variability in each of our lakes, the fact that they're not all similarly clumped together. So taking a look at our moderate scores, a good example of that is Francis Point wetland located in Georgian Bay. So our moderately scoring wetland sites generally had 2 to 3 poorly scoring sub-indicators. So in the case of Francis Point, there's low conservation capacity, essentially no conservation capacity, and also a low migration potential, just because of the hydrogeomorphology of that location. However, being in Georgian Bay, it does have a fairly high biological condition as well as a landscape condition. So this gives us a good idea of what we can do to improve the adaptive capacity of this location, and that would be improving its conservation capacity. With respect to sites scoring highly for adaptive capacity, there's a couple good examples. One of them that I think is probably the most interesting, though, is Long Point wetland. So most people are fairly familiar with Long Point wetland. It's a great migratory place for birds, and it does have conservation capacity. It actually scored fairly high for most of the sub-indicators that we looked at. However, because it's a sand spit, the surrounding landscape condition is more just what's further inland, because it really is sort of trapped by the water surrounding it. So it's a good example because it shows us that even sites that are getting a really high scoring still have room to improve their adaptive capacity. So just because there's a green dot on maybe the wetland that you're interested in doesn't necessarily mean that it has no room for improvement with regards to adaptive capacity. Just relatively compared to the other sites, it is scoring much higher. So for example, in the case of Long Point wetlands, it could be improved through the treatment of Phragmites for biological condition, through increased conservation capacity, and also potentially through improving the surrounding landscape condition. So the results of this analysis, the next step, while they can be used independently, the next step is for them to be combined with the sensitivity results that Greg was showing us in the presentation earlier today, and using these to be able to identify the vulnerability of the 20 wetland sites that we looked at. However, it is important to understand that looking at just the raw information going into assessing adaptive capacity can very much help with informing wetland resilience management strategies. Okay, thank you.
Thank you for the great presentation, Morgan. I'm sure there are lots of questions from the audience, so please continue to input your questions in the Q&A. Our first question is, it appears that for several indicators, adaptive capacity was assessed within and surrounding the wetland sites. How much of the surrounding area of the wetlands were evaluated, and what was the rationale for selecting this spatial scale?
Right, so we actually tested out at several different spatial scales. So we looked at 2 kilometers, 5 kilometers, 10 kilometers, and we also looked at watershed analysis. And what we ended up finding with using just a basic buffered approach, number one is that we were limited to within 10 kilometers based off of the data that we had available to us. We were using basically a coastal classification. But in comparing the 2 kilometers, 5 kilometers, and 10 kilometers, there wasn't a substantial difference in the percent coverage of the classes that we were looking at. So we ended up selecting the 5 kilometer metric, because it wasn't statistically different from the other ones, but also the larger scale 10 kilometer option was starting to get clipped out and extending beyond the data that we actually had available to us. So we also wanted to look at, I think the other part of that question was maybe why are you looking at within and surrounding? And the idea behind that was that something surrounding the wetland is a potential impact factor, but something within the wetland is a known impact factor. A good example for that would be the Phragmites. So once Phragmites has infiltrated a wetland, it can start to really affect the ecosystem services that are being provided. The best example of that is how it influences biodiversity. However, if you don't have Phragmites within the wetland, but it's nearby, there's a high likelihood of it being invaded. So they do need to be sort of weighed differently.
That's very interesting. Thanks for the clarification, Morgan. And I'll pose the same question I posed to Greg Grabus. Are there any additional indicators of coastal wetland adaptive capacity that you think are important but weren't able to include in your assessment?
Definitely. There really are so many things that can be included in analysis like this. And I would say, that's part of why I really wanted to emphasize those variables to understand some of the limitations that we were working with, being time frame, making sure that the sampling was consistent across all the sites. However, some of the indicators that we explored looking at but were unable to include things like water quality, vertebrate or invertebrate species richness, which I think is an important thing to include in the future. But again, the amount of time and sampling effort required to collect that data was outside of the scope of the time that we had. I think that it would be really interesting to look at more of what the impacts of the surrounding landscape could be and do that on a finer scale as well. Maybe that's just my GIS showing though. Yeah, there's definitely a lot of different things that we could factor into this. I think part of the logic that we put into it though was that bigger things are gonna hit harder. While it might be important to look at, what how many Daphnia exist in a wetland, what's probably going to impact it more is if there's a highway running through it. So there is definitely varying degrees. And although maybe there's a lot of important things to look at, there's things that are going to have a larger impact. And we tried to focus on those.
That's great. Thanks, Morgan. And we have a question from Jeff regarding the conservation capacity indicators. Can you explain the inputs a bit further? How much of this is regulatory policy related? He thinks that the provincial policy statement in Ontario would afford a protection within 120 meters, but this may not afford physical protection to other physical variables. So what exactly is the protection indicator looking at?
So that's using CPAT. And the idea behind that was that, again, looking at the spatial scale and the resolution of the data, we're well aware that there's, different protection and different protection statuses. However, in order to keep things as simple and comparable as possible, we chose the most robust data set that we could. Thanks, Patrick. So Canadian Protected and Conserved Areas Database.
Wonderful. Hopefully that answers your question, Jeff. And thanks, Patrick, for chiming in. Our last question for you, Morgan, before we move on to Patrick, our final presenter for the day. Any results that surprised you at all, similar to what I asked to Greg Grabus, or did they unfold as expected?
Yeah, so I will say that we did do a bit of an iterative process for calculating this composite indicator. Putting together composite indicators can be a really complicated thing to do. So there was actually quite a few results that I thought were really interesting. One is that I didn't expect Georgian Bay to show up having some of those moderate adaptive capacity scores. I think sometimes when we think about areas like that, we think, oh, well, there's less people up there, therefore, there's less of an impact. But looking at aspects such as migration capacity for the wetlands, I think was a really important thing to consider and include, because it adds that, some of those things that are going to reduce adaptive capacity that maybe we don't always think about. We often just think about how humans influence wetlands, but there's aspects of their hydrogeomorphology and of their structural plasticity that are going to impact their adaptive capacity that I really kind of got an opportunity to explore with this kind of study.
It's very interesting. Thanks for sharing, Morgan. And with that, we will now move on to Patrick's presentation. So let me just briefly introduce Patrick and invite Patrick to go ahead and share his screen whenever he is ready. So Patrick Rivers recently assumed the role of Habitat Stewardship Program Coordinator for Species at Risk in Ontario region with the Canadian Wildlife Service. In his former role, Patrick coordinated many aspects of its vulnerability assessment, including the collection of field data, the development of methodologies for evaluating climate change sensitivity and adaptive capacity, and assessing overall vulnerability. Patrick holds a Bachelor of Science from the University of Waterloo, a Master's of Environmental Science from the University of Toronto, and is currently pursuing a postgraduate certificate in GIS for environmental management. Welcome, Patrick, and thanks again for joining us. I see that your slides are up and in full presentation mode, so you're all good to go.
All right. Thanks, Sharon, for that lovely introduction. Yeah, so this afternoon, I'm going to discuss our methodology for combining our sensitivity and adaptive capacity assessments to characterize the climate change vulnerability of coastal wetlands. And after that, I'll be discussing trends and vulnerability scores between the climate scenarios Greg Grab has touched upon earlier, as well as trends between Great Lakes basins and wetland types. I'll then conclude by just briefly illustrating how the results of our vulnerability assessment can be applied to identify options for enhancing climate change resilience. But again, without giving too much away for the webinars to follow later this week. And just before I advance my slide here, only my name, I realize now only my name is on it, but that's certainly not representative of the intellectual horsepower behind this initiative. If I had have included everyone that can contribute to this study from all 4 branches, I probably would have needed 3 or 4 slides. Okay. I apologize in advance if my eyes are shifting because I got like 3 monitors on over here. So, okay. So to start off, I think it really does bear repeating exactly why we should be concerned about the vulnerability and fate of coastal wetlands under a changing climate. In case my colleagues haven't already convinced you, coastal wetlands are really, they're just essential for life along the Great Lakes. Existing where land meets water, coastal wetlands offer unique habitats for fish and wildlife. Hundreds of plant species call coastal wetlands their home, as well as 155 different birds, over 30 different amphibians, and 80 species of fish, many of which are sport fish. These species and the diverse communities they form filter our drinking water, they feed our communities, they fortify our shorelines, and they help regulate our climate. And coastal wetland wildlife and the diverse communities they form also attracts those seeking to birdwatch, fish, or simply get outdoors, all of which have positive economic outcomes for both Canada and the United States. However, despite our love of wetlands, or at least my love of wetlands, we haven't learned how to take care of them quite well, and quite frankly, we're running out of time. We continue to degrade, fragment, and destroy coastal wetlands, and climate change is only making matters worse, or at least complicating the situation. Coastal wetlands are responding to climate change in ways that are hard to predict and difficult to understand. So to confront these challenges and start planning for future conditions rather than past conditions, Environment and Climate Change Canada completed an integrated vulnerability assessment for coastal wetlands. And the objectives and outcomes of this assessment, which are being shared with you throughout this week, are a better understanding of the coastal wetlands that are most vulnerable to climate change and why, the development of solutions for enhancing coastal wetland resilience, and improved awareness amongst the Great Lakes community on the severity and locations of projected climate change impacts, as well as building consensus on priorities for action. So in addition to raising awareness and building consensus, my job today is really to expand on the first bullet by building upon what my colleagues have already shared. And by now, hopefully, you have a rough understanding of what makes a wetland sensitive to climate change and what preconditions and characteristics can support a wetland's ability to adapt. But knowing what actions to take and where to prioritize those actions may still be a little unclear. So I'm going to walk you through the vulnerability index we developed that combines these two elements and supports the establishment of priorities for enhancing resilience. And so this is a familiar slide shared by my colleagues, but basically I'd just like to reiterate to get a better grasp on the climate change problem. We broke it down into a framework consisting of smaller, more manageable parts. And when doing so, we followed in the footsteps of our colleagues in the US, who published a guide on conducting climate change vulnerability assessments for habitats and species over a decade ago. And under this framework, we describe vulnerability as the degree to which a coastal wetland is susceptible to and unable to cope with the adverse effects of climate change. And we further break it down into two initial components: potential impacts and adaptive capacity. Potential impact is the exposure of a wetland to a changing climate, and it is a combination of the exposure of a wetland to a changing climate and the sensitivity or responsiveness of a wetland to those changes. The elements of climate change exposure, including our climate, lake level, and coastal wetland modeling were reviewed during yesterday's session, and Greg and Morgan just gave excellent presentations on sensitivity and adaptive capacity, respectively. But when rolling up sensitivity and adaptive capacity into an index of vulnerability, we really do have to fully understand what the outputs of each assessment are and what their basis of comparison are. So in our sensitivity assessment, the basis of comparison is the simulated past or a hindcast. The simulated past was compared to the projected future under two climate scenarios to score and categorize 5 habitat or ecosystem attributes and produce an overall sensitivity index. On the other hand, for adaptive capacity, as Morgan just described, this was not based on any predictive modeling. Preconditions and natural characteristics of wetlands were compared across our 20 study sites, and scores were established for 4 sub-indicators and rolled up into an overall composite indicator. Again, another familiar slide, but with regards to the climate change scenarios considered, as with our sensitivity analysis, climate change vulnerability was assessed and will be expressed here today as a range between 2 climate scenarios under representative concentration pathway 4.5. And RCP 4.5 is an intermediate greenhouse gas concentration trajectory where emissions peak around 2040 and then slowly decline. And from the ensemble of climate projections associated with RCP 4.5, those at the lower bound or bottom end of the ensemble predict average lake levels similar or slightly lower than the long-term average across most of the Great Lakes Basin. Whereas on the upper end, as Greg Gravis articulated, average lake levels are predicted to be higher than the long-term average, and there's greater incidences of extreme high and low water level events. And so to categorize climate change vulnerability, we initially considered using a logic model or matrix that combined the categorical results, so that's the high, moderate, and lows of the sensitivity and adaptive capacity analyses into a matrix as illustrated here on the bottom right. So this approach has been applied in many climate change vulnerability assessments for habitats and species, and it's at the foundation of NatureServe's Habitat Climate Change Vulnerability Index. And so here, a low resilience score, which considers adaptive capacity, is combined with a high sensitivity score to achieve a very high habitat climate change vulnerability. So you end up on the bottom left-hand corner of this matrix. And then conversely, a high resilience score combined with a low sensitivity score reaches low vulnerability. So you find yourself here in the upper right-hand corner of the matrix. However, as you may recall, several of the coastal wetlands we assessed were categorized as having moderate sensitivity, and at risk. particularly under the lower bound scenario. So as we began to put our sites through this matrix, it became apparent that adaptive capacity categorizations were often dictating what the overall vulnerability of a wetland would be. In other words, through this matrix, sensitivity scores were almost giving a neutral vote, and often adaptive capacity categorizations were swaying the vote one way or the other. And we didn't feel this was appropriate given the volume of science and research at the foundation of the sensitivity assessment, and considering by definition that a moderate sensitivity does equate to a risk towards the continued delivery of wetland ecosystem services. And so to address this issue, we adopted a more quantitative approach, only slightly, not a lot of math involved, where sensitivity and adaptive capacity scores were added after some minor adjustments to each data set. So the first step was inverting adaptive capacity index scores to ensure consistent directionality between the two subcomponents of vulnerability. Currently, a high adaptive capacity score, or a score approaching 1, is, for lack of a better word, a good thing, right? This is a wetland that's highly adaptive, whereas the opposite's true for the sensitivity index. A score approaching 1 is, again, lack of a better word, a bad thing. This is a wetland that's extremely responsive, and negative impacts are projected. So reversing one of the indices just ensures that the two won't negate each other when they're added into an overall composite indicator. The second step was rescaling the sensitivity index scores to ensure equal weighting. So it was decided that scores less than 0.1, so that 10 percentile threshold that Greg Gravis explained, should be rescaled to 0, as this implies there was a minor wetland response to water level change, virtually normal conditions, and minor, if any, projected impacts and risks to the continued delivery of wetland ecosystem services. The third step was to rescale scores greater than 0.1 on a continuous range from 0 to 1. And again, this was done to ensure equal weighting between the two indices when combined. Basically, what we wanted to ensure is that the adaptive capacity results weren't overshadowing the results of the sensitivity assessment, particularly for wetlands that were highly responsive or considered to be critically at risk. There we go. And so in the fourth step, the two indices were combined or added to arrive at an overall index of vulnerability ranging from 0 to 2, 0 being very low vulnerability and 2 being very high vulnerability. As a fifth step, vulnerability index scores were classified into 5 levels using equal intervals, where green equates to very low vulnerability, yellow, low vulnerability, orange, moderate, red, high, and dark red, very high. Waiting until the final step before classifying or bucketing index scores is recommended when developing a composite indicator, as it limits the amount of generalizations or unintentional weighting and increases the resolution of the final product. In our assessment, we also wanted to have numerical and categorical scores to ensure direct comparisons could be made when setting priorities for enhancing resilience. Okay, so now that I've given a rough overview of our methodology, I'll go over the categorical results of our vulnerability assessment, starting with trends by climate scenario. And again, as with our assessment of wetland sensitivity, each of these scenarios are equally plausible and can be used to inform management. So under the RCP 4.5 lower bound scenario, the majority of the coastal wetlands we were evaluated as having low to moderate vulnerability. Sites with moderate vulnerability are most concentrated in the Huron-Erie corridor and the southwest end of Lake Erie due to their low adaptive capacity and moderate sensitivity. Interspersion was responsive and evaluated as at risk across all 4 of these locations, which could equate to decreased population density among marsh birds. And obviously, This is obviously of concern given the importance of this region for staging and feeding migratory waterfowl. Jordan Station Marsh was the only wetland to be considered highly vulnerable under the RCP 4.5 lower bound scenario, given its low adaptive capacity and moderate sensitivity. Plant community diversity in Meadowmarsh area were highly responsive and evaluated as critically at risk at this location, which could lead to decreased ecosystem function, stability, and the delivery of important wetland ecosystem services like nutrient cycling and food production for wildlife. Okay. And so under the RCP 4.5 upper bound scenario, the majority of the wetlands we examined had moderate vulnerability or higher. Sites within the Huron-Erie corridor at the end and the southwest end of Lake Erie have been elevated to very high vulnerability due to increased sensitivity. Wetland area in particular was highly responsive and evaluated as critically at risk across these 4 locations. Should this transpire, a number of important wetland ecosystem services could be compromised, including wildlife habitat, shoreline stability, and water quality improvement. And as Greg Gravis mentioned at the conclusion of his talk, here projected wetland losses can likely be attributed to elevation and land use. This region is sort of a sand clay plain with very gradually sloping shorelines, which can translate into significant flooding during a high water level event, which some of you on the call may have experienced firsthand. And with a lot of the shoreline developed here, as well as upland environments converted to agricultural or urban centers, these wetlands may be unable to migrate landward and seek refuge as water levels rise. Okay, so that was a very high level overview of the results by climate scenario. And now I'll review some vulnerability trends and observations made within each of the Great Lakes basins, starting with Lake Huron and the St. Mary's River. Okay, so the map on the right-hand side here communicates vulnerability across our sites as a range, where the left-hand side of each site circle is relative to the RCP 4.5 lower bound scenario, and the right is relative to the upper bound scenario, or the, for lack of a better word, the wetter scenario. And the colors associated with vulnerability are represented here in the legend in the upper right-hand side. So across the 7 wetlands we looked at in this basin, lower bound vulnerabilities range from very low green in Treasure Bay to moderate orange in Anderson Creek Marsh on the North Channel, St. Mary's River region. Upper bound vulnerabilities range from low across multiple locations to high red in Whiskey Harbor. And unfortunately, I don't really have the time to rationalize each wetlands vulnerability evaluation, but we'll take a closer look at 2 sites, Anderson Creek and Treasure Bay, to understand some of the differences between between each evaluation. So both of these wetlands, as Morgan described, have a high landscape condition and biological condition, and they're both located in the Canadian Shield, which is a region characterized by impermeable exposed bedrock and higher elevation, higher vertical relief compared to the Southern Great Lakes for sure. And because of this, the potential for wetlands to migrate upland as water levels rise can be restricted, leading to wetland loss. However, under the RCP 4.5 lower bound scenario, where lake levels are predicted to be stable or drop, it's the ability of a wetland to migrate downslope that confers resilience here. Because Treasure Bay is situated in a protected embayment along Eastern Georgian Bay, it was evaluated as having a higher downslope migration potential than Anderson Creek. In fact, the area deemed suitable for downslope migration was nearly 300% of its original footprint. Anderson Creek, on the other hand, is a drowned river mouth wetland open to the coastal processes of the St. Mary's River / the northern channel of Lake Huron. And this can be expected to limit its downslope migration potential. The area deemed suitable was actually only 55% of its current footprint. For these reasons, Let me just step back a sec there. So for these reasons, and considering Treasure Bay is also partially protected by Georgian Bay Islands National Park, Anderson Creek was evaluated as being less adaptive, more sensitive, and therefore more vulnerable to climate change than Treasure Bay under the RCP 4.5 lower bound simulation. Now we can move on to the Huron-Erie corridor. So I've already kind of spoken to the wetlands within this basin, but as Morgan expressed, most of these have low adaptive capacity. And as Greg expressed, they're highly responsive to changing water levels. Along the eastern shoreline of Lake St. Clair, there's a lot of dikes and drainage infrastructure protecting agricultural lands, impounded wetlands, and coastal properties. And we expect this to challenge the ability of wetlands to migrate landward as water levels rise, leading to net losses in wetland area. And a similar phenomenon is projected to occur along the Detroit River, but here it's obviously urban encroachment and shoreline armoring that's creating the problem. Vulnerability evaluations on Lake Erie were very highly variable, as you can see on the map on the right. Lower bound vulnerabilities range from very low green, Selkirk Provincial Park, to moderate orange in two locations, Fox Creek in the southwestern end and the Grand River mouth as well. All locations in Lake Erie were evaluated as having moderate vulnerability on the upper bound simulation, with the exception of Fox Creek, which was evaluated as being highly vulnerable. In fact, Fox Creek is considered to be one of the most vulnerable coastal wetlands assessed due to its low adaptive capacity and moderate sensitivity. Its biodiversity and ecological resilience have been pretty compromised by dense stands of invasive Phragmites within the marsh, and it's also situated in a highly agriculturalized landscape, which has had an adverse effect on habitat quantity and quality. As you can see in the image here, the really grainy image, upland development as well as coastal processes are expected to limit this wetland's ability to migrate through lake level variability as well. And this has been somewhat substantiated by the results of the sensitivity analysis, where multiple habitat ecosystem attributes, including total wetland area and the volume of submerged aquatic vegetation, were evaluated as critically at risk. And this could jeopardize the continued delivery of a number of ecosystem services, including water quality improvement, but also spawning, nursery, and foraging habitat for fish, reptiles, and amphibians, including many of those species at risk indicative of the Lake Erie Basin. Now, Long Point was evaluated as having moderate vulnerability under the RCP 4.5 upper bound simulation due to its high adaptive capacity. But as Greg pointed out, it was evaluated as highly responsive and critically at risk through the wetland sensitivity assessment. And in particular, meadow-marsh area and interspersion were highly responsive, which could decrease the amount and quality of habitat available to marsh birds. And much like the eastern shoreline of Lake St. Clair, this is obviously a big concern given the importance of this internationally recognized wetland complex for staging and feeding migratory waterfowl. And high sensitivity evaluations for this wetland can be rationalized by the unique topography of Long Point. You can see the steep sand dunes along the peninsula here in the image on the bottom right. And then as you move closer to mainland Norfolk County on the Long Point Peninsula, shoreline development may challenge landward migration as water levels are with projected rises in lake levels. So lastly, we land on Lake Ontario and the upper St. Lawrence River. And these evaluations were also highly variable. Upper and lower bound vulnerabilities range from very low green across multiple locations to high red, again, as seen in Jordan Station Marsh. And so under both climate simulations, Jordan Station was evaluated as having high vulnerability due to its low adaptive capacity. High agricultural development in the 20-mile creek watershed on the Niagara Peninsula has decreased habitat and water quality conditions within Jordan Station. And as you can see on the image in the upper left, steep embankments near the mouth of this marsh really limit the ability of remaining wetland habitat to colonize upland environments should water levels rise. Moving over to Lynn Creek in Whitby, Ontario, it's also challenged by land conversion, but in the form of urban development. The upland environments west and north of Lynn Creek are expected to offer some refuge for wetland plants during high water level periods, but multiple ecosystem attributes, including total wetland area and meadow-marsh area, were responsive and considered to be at risk under the RCP 4.5 upper bound scenario. Okay, so despite that pretty quick high-level overview of vulnerability across the baselands, I hope you now have a better sense of what to expect in terms of the vulnerability of coastal wetlands to climate change and how we came about those conclusions. And so for the last few remaining slides here, I'd just like to discuss or present ways in which these results can be applied to prioritize options for enhancing the climate change resilience of Great Lakes coastal wetlands. So throughout our assessment, we developed a guidance document containing novel adaptation strategies, measures, and options for enhancing the climate change resilience of coastal wetlands. And in addition to our assessment results, this document was informed by stakeholder and expert feedback, extensive secondary research, and insights gained from a multi-agency advisory committee. And all of this yielded 6 broad adaptation strategies with 17 associated measures and over 160 options for enhancing climate change resilience. These will be discussed at length over the coming days, but I'll touch upon a few of them in the slides at the slides to follow. So by examining the components of vulnerability evaluated in our assessment, we can identify measures and options that address the potential impacts and adaptive capacity gaps identified. So on the left-hand side of the slide here, we have a summary of vulnerability for Hog Bay, which is an embayment within Severn Sound Lake Huron that still has a considerable amount of upland natural habitat intact. However, wetland losses were projected through our sensitivity assessment, and this location remains to be formally protected as measured through the Canadian Protected and Conserved Areas database. So to enhance the climate change resilience of Hog Bay, it would be prudent to consider options that conserve and restore landscape connectivity. And this could be achieved through land use planning, such as the establishment of protection or buffer zones in adjacent upland habitats, or by modifying existing bridges and culverts to reestablish hydrologic and habitat connectivity. So these and other options will be discussed as part of strategy 1, which is upcoming during tomorrow's webinar session. Moving to Lake St. Clair, within the marshes of Eastern Lake St. Clair, a number of ecosystem attributes were evaluated as being highly sensitive and critically at risk under the upper bound scenario, which again is a wetter future. High land conversion and the expansion of invasive Phragmites are also expected to limit the ability of this coastal wetland complex to adapt to climatic disturbances. And so to enhance the climate change resilience of Lake St. Clair, it's necessary to consider options that address local dikes and drainage infrastructure, protecting agricultural lands, coastal properties, and wetland impoundments, as well as the management of Phragmites. And these types of options will be discussed during our 4th session on Thursday. Okay, so much like Long Point, Orondo is a large sandspit embayment on Lake Erie, and one of its greatest threats is the loss of a barrier beach protecting vulnerable coastal wetland habitat. And over the past 60 years, regional disruptions to littoral sediment transport have yielded significant loss in wetland habitat, as illustrated by the figure here in the upper right. So measures for managing shoreline erosion under a changing climate and restoring natural littoral sediment transport will be discussed by Peter Zuzek of Zuzek Inc. during tomorrow's webinar session. Okay, the last example I'll give is of Hill Island, just because I feel like the St. Lawrence River always gets neglected in our discussions. So Hill Island is within 1,000 Islands National Park. And much like the coastal wetlands in the Canadian Shield, the exposed bedrock at this location is expected to challenge the ability of wetland plant communities to colonize upland environments during periods of high water levels. And a particular concern is small, unique meadow marshes that exist at this location. So options for maintaining or restoring wetland biodiversity including enhancing existing plant community structure and native species populations will be discussed during, I believe, Thursday's session. Okay, so that's about all the time I have for today. I think I've actually gone over my time, but I'd just like to end off with a few conclusions, some of which have already been raised by my colleagues. So among the locations assessed among the locations in our assessment, coastal wetlands appear to be more sensitive and therefore more vulnerable under a wetter future. So that's associated with RCP 4.5, with the RCP 4.5 upper bound climate scenario. And preconditions such as land use and natural characteristics like geomorphology and biodiversity can increase vulnerability, or they can confer resilience. It can have a positive or a negative effect. And generally, coastal wetlands in the Huron-Erie corridor and the southwest portion of Lake Erie appear to be the most sensitive, least adaptive, and therefore the most vulnerable. And it's, as Greg Gravis pointed out at the end of his talk, it's reasonable to assume coastal wetlands with similar climatic exposure, geomorphology, and land use share similar sensitivities and vulnerabilities, but caution really needs to be exerted if and when extrapolating the results of our assessment beyond the study sites we looked at. And management should really be informed by a careful examination of each component of vulnerability and the different subcomponents too, as well as local valued ecosystem attributes and local management capacity. Again, these themes will be discussed in the sessions to follow later this week. And lastly, and perhaps most importantly, there are actions that can be taken to enhance the climate change resilience of all coastal wetlands assessed, even those that we've evaluated as having low vulnerability. And so with that, thank you. I hope I held your attention. I hope you learned a bit. And I hope you feel inspired too. I don't want those listening to walk away feeling complete doom and gloom. Our assessment of climate change vulnerability has certainly identified real risks to the conservation of coastal wetlands, but it's also identified ways or opportunities in which we can enhance their resilience and ensure their long-term conservation. So I guess in summary, there is a lot at stake, and the time to act is most certainly now. So thanks again, and I'm happy to answer any questions now, as well as during the panel discussion to follow.
Great presentation, Patrick. And I love all of the photos. I think our participants yesterday were very interested in seeing more photos. So I'm glad you covered it today. We are running a bit late. So why don't I now invite Greg Main, Greg Gravis, and Morgan to join us for our panel discussion. And we will save questions for your presentations to the panel discussion as well. Wonderful. And so the first question is to Greg Main. Through your discussions with conservation practitioners locally, was there interest in using the vulnerability assessments to inform adaptation on the ground?
Most definitely. Absolutely. Plenty of opportunity. As Patrick said, we shouldn't walk away from this feeling doom and gloom. We have an incredible selection of conservation authorities and NGOs and local stakeholders with a huge interest in coastal wetlands, who are all very interested in applying the results and their own results of their own studies to improve coastal wetlands. So we've had a number of discussions with conservation authorities and other local stakeholders, plenty of opportunity and lots of enthusiasm.
That's wonderful. Thanks, Greg. And Patrick, it was clear through your presentation that through the assessment, it's possible to identify what's driving the vulnerability scores to help identify specific adaptation strategies. Have adaptation strategies been identified for all 20 wetlands, or is this part of future work?
Yeah, so I mean, that's part of the ongoing discussion and will likely be an outcome of the sessions to follow throughout the rest of the week. What I illustrated there was sort of my own preliminary screening level assessment. But I think to really go down that path, there has to be, as Greg Main just pointed out, engagement with the stewards of those marshes, right? To identify what they value most and what their management capacity is, right?
And their own goals.
Exactly.
Every wetland is different, and every wetland is managed slightly differently, depending if fish is a focus or wetland birds are a focus, or reptiles and amphibians. So everyone has a slightly different interest and need, and so adaptation strategies and adaptive measures have to be tailored to the local situation.
Absolutely. Great to hear, Greg. And Greg, I just want to go back to a question we received from Mary earlier about the selection of the coastal wetland study sites. I'm just wondering if you could share with us briefly how the 20 wetland sites were selected, and were there any shield wetlands, particularly in Georgian Bay, that were included?
I could give my answer, but I actually think, Patrick, if that's okay, I'll pass this one over to you, because you really did a good job on, and Greg Gravis, you did a very nice job on a summary document of why we selected the wetlands. So I think Patrick and Greg Gravis are really well situated to answer that question.
Do you want to go first, Pat?
Sure. Yeah, well, I mean, I think as Mary knows, we definitely undertook a concerted effort to survey and predict the vulnerability of the marshes within Eastern Georgian Bay. We had we did collect actually vegetation and had candidate sites within Tadanac Bay, and we also had a site in the Key River. But I think what it came down to in the end was limited LiDAR and elevation data, right? If you attended yesterday's session, I'm sure you know that the digital elevation models are at the foundation of all of this, right? And high resolution DEMs at that too, right? We're talking 2 meters. So we just weren't able to obtain that information for those marshes and accurately model their upland elevation and model their elevation at a resolution needed to predict and evaluate coastal wetland response.
Yeah, I read the question as well, and maybe the response would, for that question, then maybe others that are wondering about site selection across the Great Lakes. So I think the original question asked if we thought that the results were skewed because it didn't include a certain suite of wetlands in Eastern Georgian Bay. And I think the whole idea of skewed kind of brings up the idea that we tried to generalize across landscapes. And I thought it was pretty evident from at least my presentation that the more we got into the project, the more, at least I think, that we found that the results we found were pretty site specific. So there was no real effort, number one, to generalize across the Great Lakes, because I mean, there's over 1,000 coastal wetlands across all the Great Lakes, and that's a low estimate too, right? It doesn't include a lot of Eastern Georgian Bay wetlands, as well as wetlands less than 4 hectares large. So there are a lot of wetlands out there, and picking 20 out of 1,000, I wouldn't say that it skews anything. I'd say that a lot of wetlands, a lot of sites, a lot of systems are underrepresented. We're underrepresented or not represented, right? There's some, and this is for everybody. There are a lot of jewels on the Great Lakes that we just couldn't kind of assess with this. Point Pelee, Matchdash Bay, Coots Paradise, Presqu'île Provincial Park. There's a lot of great sites on there that I would love to run and get information on these analysis from, but we just couldn't. I mean, it is a bit of a gut punch too, to me anyway. There was 7 sites in Lake Huron, 20 overall. I don't think we would have put 10, over half the sites into Lake Huron. I get, sites where we're not represented. But I think what it really comes down to is we did the best we could with what we had in the time allowed. Though that's as Marianne mentioned yesterday, some of these analyses took 2 and 3 weeks to run. Given the absolute amount of investment that went into these, and considering, we did have to drop Lake Superior, only had one site on St. Lawrence River, none really on St. Clair River proper. I think we had some pretty good coverage across the Great Lakes. And of course, yeah, again, we missed some spots, but I think what we have is an excellent product.
That's great. Thanks, Greg and Patrick and Mary. I hope that this answers your question. If there are any follow-up questions, please do follow up with us in the Q&A. And if we're unable to address your questions at this time, we will definitely follow up with written responses from our speakers. So I did want to take this opportunity to dig into Patrick's concluding point about scaling the vulnerability assessment to other wetland sites. So our question refers to Greg Grabus and Morgan First, perhaps, is what are some of the easily transferable aspects of the sensitivity and adaptive capacity assessments that could be easily transferred to other or replicated at other wetland sites? So Greg Grabus, if you don't mind going first.
Yeah, sorry, I have to be honest. A lot of times I don't understand exactly what the question is. A lot of times I get so invested in what we did do. It's hard to explain maybe what we didn't do or what we could do. But as far as applying this framework to other sites, my understanding is it can be done. We know across the Great Lakes what elevation different vegetation taxa occur at. I know the Meteorological Service team has created lake models. So we have a lot of the data to go off of, but you might need probably additional vegetation data at sites that weren't completed. Definitely you'd need elevation data in terms of above the water, so topographic data, as well as those underwater contours, the bathymetry. And then, and that's just for the sensitivity part, well, for obviously the modeling part and the sensitivity, but I think there are pieces there and you'd need to augment more. I hope that answers the question, Morgan, or I do know you can add to that. So if you could, please.
Yeah, like I can definitely speak to adaptive capacity. I think that some of the challenges that would be for translating sensitivity are just the amount of work that it takes to get those coastal wetland response models and to do all those amazing calculations in order to assess sensitivity. On the other hand, adaptive capacity is a little bit more mobile. And I think that there's 2 ways that you could use those results to look at wetlands that weren't included in the original 20 wetland sites. Number 1, you could look at, how do sites directly compare to the 20 that we looked at? Like, do they have similar landscape coverage surrounding them? Do they have similar coverage of Phragmites? Like, you can kind of draw connections that way. I know I mentioned this in the presentation, though. One of the main things to consider with adaptive capacity is that it is relative. So those scores are based off of what was put into our calculation. So I think that it lends itself very well to being recalculated with additional sites, especially considering that most of the information used in it was geospatial data. The main limiting factor would be site visits to assess vegetation species richness, but something like that, if it can be redone for multiple sites, you could essentially rerun that calculation and get potentially a broader scale for adaptive capacity across sites that you would add to it. Hopefully that answers the question.
Does. It's very helpful, Morgan. And Patrick, anything you'd like to add, knowing that you've been very close with the methodology as well?
Nothing really earth-shattering to add. I think Morgan summarized it well. I think like the components that are scalable, they're the ones that can be analyzed through remote sensing, right? Like at this time, like it's too, cost and financially prohibitive to maybe undertake some of the aspects of this sensitivity analysis and scale them up. But, that being said, like the advances in, the physical and hydrodynamic modeling made through this project undertaken by the Meteorological Service. Like that's a super valuable product to have. And I think there is the potential to take that and apply it to other wetland sites in the future for sure.
Yeah, just to build on that, Marianne did kind of answer that question yesterday. It's not an inconsequential task developing the digital elevation models and all of the various models that she explained yesterday. It would take quite a bit of time in the matter of weeks. I mean, maybe that doesn't mean a lot to a lot of people, but for the people running the models, it's a 16-hour day. So, oh, there's Marianne. So I see Marianne has joined us. Oh, that's interesting.
I just want to say everything depends on what is already available. For our perspective, to have a new site, the most limiting thing is the digital elevation model. So if we have nothing regarding the digital elevation model, we talk about months. I will say about 6 months. And it's depend if it's the winter or the summer. So to get the field data. But if we already have good bathymetry and that we can get some of that bathymetry and topography and we can work on it, it can be faster. Or if the digital elevation model is available and it's can be corrected for the really dense emergent marshes, for example, we can already run what we have for the hydrodynamic, the wave model, and we can use the wetland succession model that was developed in the other side of the same lake than the new site, and apply it and try to validate it if we already have vegetation data. So I would say it depends on the condition or of what is available at the moment that you were saying to me, okay, I want that site. So something from 3 months to a year for a new site.
Thanks for joining us, Marianne, and for chiming in, Greg, Maine, and Patrick. And while we have Marianne on the line,
yep.
Perhaps we can revisit Harold's question in the Q&A. Do the models predict how many new wetland areas would be created if the trend is towards higher water levels? That is where there currently are no wetlands, but would be with more flooding. So does the wetland modeling tell us where new wetlands might be created?
Quickly, yes, but it's site specific. So what the wetland succession model can give you, it's how the wetland distribution is changing according to a rising or going down model. So for every site that we're studying, we created what we call an area of interest. We didn't present that yesterday because it's kind of methodological, but we look at, we select an area where it's possible that the water level will go according to the climate change scenario, so that we can limit calculation. Because if you just choose like 20 kilometers around the wetlands, it's going to take time to calculate everything. So we choose an area of interest. We delimit that area, and it's possible for the wetland to migrate according to the water level. But there, like we explained yesterday, there is land use that blocked the migration, or there's the type like bedrock in Huron Lake, it's blocking the migration. But I will give an example like with Lake St. Clair. It's a really diked area. So it will be possible to take the wetland model at this place and say, okay, we take off the dike, and the area of interest for this lake is really big for this wetlands because it's really flat. And we can give different value to different crops where it's possible for the wetlands to migrate 2 times. And we can see, okay, so if we choose to take off the dike, what's going to be the wetlands according to the climate change scenario, or just with what we forecast. I hope I'm answering to you, Mr. Lee.
Yeah, and maybe I'll just add quickly to that too. And Harold, that's a great question, because we've kind of considered that in the past, that there are. I mean, Marianne answered the question in the context of our sites, but there are areas obviously around all the Great Lakes that are low lying, where there aren't wetlands, where no one can remember there being wetlands. But if there is an increase we see this increase in water levels and the variability. There could be areas that weren't inundated in the past, but then are and become wetlands. So, and this study did not, we couldn't consider that. So some of the losses or periodic losses we see in wetlands at the study site, or that could occur at other wetlands around the Great Lakes, could actually be offset by other areas that are low-lying around the Great Lakes. You know, hopefully if they're still natural, or they'd have to be natural, I guess, and could be whatever, converted into wetlands. So that's a great point.
Wonderful. Thanks, Marianne and Greg Grabus. And I see that Harold has follow-up with what about lake-wide trends and gains and losses?
Okay, so I think I get it. So generally across the Great Lake, in terms of wetland area, total wetland area, there's a general loss of total wetland area across the sites when we look at our climate change scenario in the future. But when you look at the large wetland class distribution, such as emergent marsh, wet meadow, shrubby swamp, forested swamp, the answer is more lake, even site specific. So there are some places where you see shrubby swamp increasing or submerged aquatic vegetation. So I will invite you to consult yesterday's presentation for more details.
That's great. Thanks, Marianne. And of course, the slides and recordings for yesterday's session will be made available in a couple of weeks following the completion of this webinar series. And lastly, what are some important indicators to monitor and keep track of to measure adaptation progress? And perhaps we can start with Morgan on this one, given the focus on adaptive capacity. What are some important indicators that we should be keeping track of to help measure adaptation progress for coastal wetland resilience?
Sure. So just let me make sure that I understand. To monitor adaptation progress related to changes in adaptive capacity or related to changes in adaptive management strategies?
You can take it however you'd like, Morgan, but I was referring particularly to changes in the resilience of coastal wetlands.
Oh, okay. I mean, I think that the best way to do it is repeated measures. So looking at overall change and then how well that is correlating to the ecosystem services that are being provided. So if you could go and look at a wetland and, say measure the species diversity year after year and recognize whether or not that's declining, increasing, maintaining, something like that might be able to tell us whether or not it's actually resilient to the disturbance effects. I think it's also really important to understand that, disturbances that we notice, we often think about them being something really large or something, like a tornado is supposed to come through and then what happens because of that. But I think a lot of the changes and disturbances that we see are a little bit more insidious and gradual. So I think it would also be really prudent to take a look at what things are actually impacting these wetlands year after year. Again, invasive species is one that comes to mind right away. How quickly are these expanding? How quickly are they impacting the wetlands? And what kinds of other structural challenges can they be causing at those locations?
I'll add to that, Sharon. First of all, I hope people pay attention to tomorrow, Thursday, and Friday, because by doing so, you'll have a better insight in terms of how we might want to look ahead and monitor some of the aspects of vulnerability and resilience in general. Water quality, for instance, is one obvious one that is foundational to the health of wetlands, and it's being monitored by both Canadian and US. There's a coastal wetland monitoring program that's been established for 10 or more years, maybe even 15 now, that examines water quality. And they do have trend data. And tomorrow you'll see a graph or a map of wetland water quality across 500 different sites. So this is ongoing by a collaboration of US and Canadian partners. So that's one obvious indicator that can be used. We also have state of the Great Lakes indicators for coastal wetlands that can be used as well in terms of wetland vegetation, obligate nesting birds, amphibians, Now, and there's more. But beyond that, it's habitat connectivity. It's how well we manage a fragmented landscape, and by increasing the connectivity, both aquatically and terrestrial, and measure that, which we can do through spatial analysis over time. That's another great indicator in terms of just how resilient we can make these ecosystem attributes, but monitor them through spatial analysis over time. That's just a couple of examples. And I think that by tuning into our presentations over the next 3 days, people will have even a better understanding of the options that are available to us.
Wonderful. Thanks, Greg and Morgan. And I do want to leave all of you with the last words. So I just wanted to see if anyone has any last words before we close the webinar today to share with our participants.
Just join us over the next Wednesday, Thursday, and Friday to learn more, because you've listened to the foundational aspects of wetland exposure through climate and lake levels, wetland sensitivity through the indicators that Greg Gravis had spoke of, and wetland adaptive capacity through the various indicators that Morgan really did a nice job of expressing and conveying, and then overall wetland vulnerability. Let's see how we apply that. That's how it makes sense to the suite of adaptation strategies that we've selected, with the help, by the way, I might add, of hundreds of stakeholders, rights holders, and partners. So let's hope. I think we have it right. We've selected 6 primary strategies, 17 measures, and a whole slew of various options. But we'll try and bring those alive through various presentations over the next 3 days. And we won't be able to touch on everything, but we'll try and hit the main points anyway.
That's great. Thanks, Greg. And that does bring us to the end of our panel discussion. So I'd like to thank all of our speakers for your excellent presentations today and for your ongoing work. I would also like to thank our project team, Greg Anders and Patrick from ECCC, and Megan, Jessica, and Krista from TRCA for making this webinar possible. For questions that we were not able to cover within our time today, we will follow up with speakers for some brief written responses, which we will share along with the presentation slides and webinar recording. We anticipate that the slides and recording will be available in a couple of weeks following the webinar series, so please keep an eye out for an email. We have 3 more webinars over the course of the week. Starting tomorrow, we will switch gears, as Greg mentioned, to focus on possible adaptation strategies and options for enhancing coastal wetland resilience. Tomorrow's session will focus on reducing non-climatic stressors, such as land use change, enhancing adaptive capacity, and protecting littoral solid geodiversity and barrier landforms. And we have invited 5 guest speakers who will share some practical examples of their adaptation work with us. So we hope to see you at these upcoming sessions. Our speakers include Laura Ellis from ALUS Canada, Ralph Tonninger from Toronto Region Conservation Authority, Paul Biscaya from Credit Valley Conservation, Pete Zuzik from Zuzik Inc., and Joshua Ungeyer from the U.S. Army Corps Buffalo District. And now I would like to call on Greg Mayne to say a few last words and share some upcoming reports and resources.
Yeah, thanks, Sharon, and thanks for doing such a nice job of moderating this session and yesterday's session. I don't need to say very much. I've already mentioned this yesterday. There are a number of reports, technical and public friendly, that are coming, that are a result of all of the hard work over the last 3 years. They will be made publicly available, hopefully on the Environment and Climate Change Canada website, after they go through a very rigorous communication exercise and oversight. But we've already mentioned that Frank's work is peer reviewed, and I think manuscripts are submitted to journals. He also has a technical paper that we can make available. Marianne had expressed that they have a 460-page technical report on the coastal wetland response model and all of the various subcomponents of that. That also is going through peer review. Actually, I think it's finished with the peer review, and it will be taken through the process with communications. And then I do want to make mention again that we did work with TRCA and the Climate Change Impacts Annex to produce a a very public-friendly document, climate change in the Great Lakes Basin. And we've talked about the sensitivity as well as the adaptive capacity today. So those reports will be made available as well. Don't look for them anytime soon. As I say, they have to be approved at a high level. They have to go through communications. They have to be French translated. And then they need to be posted. So maybe by the end of this summer. And then I'll save the last two reports maybe for the next few days. Thank you very much. I mean, this has been a real pleasure. Thank you to our speakers. You guys are rock stars, fantastic presentations. And I hope people in the audience got as much out of them as I did. So with that, I'll say goodbye and thank you, and we'll meet again tomorrow afternoon.
That's wonderful. Thank you for those closing remarks, Greg. Thank you everyone for joining us, and take care.
Thanks, Sharon. Bye-bye.